So next we shall be going on to the next topic, influence line diagrams. Now as you know, as the corresponding live load or the impact load, what in some textbooks they call it, as these loads move on the bridges, they will produce different reactions, shear force and bending moments as they keep on changing the position. So a structure as such, a bridge structure must be designed for the most severest condition that can occur, okay, at a particular section. Okay, as these corresponding rolling loads move, okay, at a particular section there may be a point, there may be a position at which the corresponding section will have maximum bending moment or maximum shear force. So as such, that corresponding structure must be designed based on that maximum value. Now the best way for determining this maximum value at a section is by using influence line diagrams. Okay, so in this lecture we shall be discussing ILDs, influence line diagrams, for beams or slabs and then trusses. Okay, so while finding ILD for slabs, it is like we are having the maximum internal force. Usually the maximum internal force given by Q. The maximum internal force can either be bending moment or shear force. So for slabs, okay, the corresponding value of bending moment will be given kilonewton meter per meter and kilonewton per meter for shear force. This is for shear force and this is for bending moment. Now I hope you have already studied regarding ILDs for a simply supported slab. So as such, these are the corresponding different ILDs for RB reaction RB, reaction RA, then corresponding shear force and at a section C and corresponding bending moment at section C. Okay, so as such, at this section C, it is a distance of A from one end. You can see that minus A by L and 1 minus A by L, and A into L minus A divided by L for moment at C. I hope you have already studied this in your structural analysis class, so I am not going into much detail regarding that. And then we have for simply double overhanging. Okay, double overhanging, we have this corresponding for RA and RB. You have the corresponding influence line diagrams like this. 1 at this point, the value will be 1. And at this point, the value will be 1 at RB. And then you have the influence line diagrams for the corresponding shear force as well as bending moment at a section C, that is in between A and B. Okay. So I hope you already know this, so I'm not going into much detail. We shall directly deal with the basic concept and go for problems. So if you have a train of loads instead of a point load, okay, if you have a train of loads as such, then you will have an ILD. You will have an ILD. So in order to obtain the maximum, this ILD may be either for shear force or bending moment. Okay, so to obtain the value of that shear force or bending moment Q, in case of concentrated loads, what I will do, I multiply P1 multiplied by Y1 plus P2 multiplied by Y2 plus P3 multiplied by Y3. This you already know it, how to find the internal force, whether it is bending moment or shear force. Simply multiply the concentrated load and the corresponding vertical offset of the ILD. Similarly, in case of a UDL, if you have a corresponding load intensity Qx, the corresponding value of Q can be obtained by Q into integral XL to XR y dx, or you can say Q multiplied by the area of the ILD between these two endpoints. Okay, so if you have a simply supported structure with a uniformly distributed load, so if I want to find the maximum value of say RA here, okay, what I do, I multiply this load intensity Q and the area of the graph between these 2 points. Okay, so same concept is what is explained here. In case of a UDL, uniformly distributing load as such, that is varying with distance x. Okay, not perfect UDL, but it varies with distance x. So this is the question we shall be discussing today. 4 wheel loads of 6, 4, 8 and 5 kilonewton cross a girder of 20 meter span from left to right, followed by a UDL of 4 kilonewton per meter and 4 meter long with the 6 kilonewton load leading. The spacing between the loads in the same order are 3, 2 and 2 meters. The head of the UDL is 2 meters from the last 5 kN load. Using the influence line, calculate the shear force and bending moment at a section 8 meter from the left support and 4 kN load is at the center of span. So it feels a bit confusing. The first line itself is explaining the type of wheel load. So you have a corresponding train of loads that is going from left to right. Okay, so the 6 kN load is leading. So you have here a 6 kN. Okay, then you have 4, then you have 8, then you have 5 or kN. Okay, and then it is followed by a UDL. Okay, this is a corresponding train of loads. Okay, so the distance are 3 meter, 2 meter and 2 meter, and the head of the UDL is 2 meter from the last 5 kN load. So this is 2 meter. Okay, and this last UDL is 4 kilonewton per meter acting over a distance of 4 meters. Okay, so this is the train of loads. So the corresponding this train of loads is explained in words here. So understanding that will be a bit difficult. So as such, this is the train of loads. This corresponding train of loads is passing over a bridge, okay, of 20 meter. Okay, 20 meter. And what is the corresponding shear force and bending moment at a section 8 meters? Okay, at a section 8 meters from this one left edge, say this is section C. Okay, at a particular point when this corresponding 4 kN load is acting is at the center. Okay, this 4 kN load is at the center. I shall draw the beam once again. The distance, it is 20 meters. Okay, this is the center, and I require the corresponding bending moment and shear force at a distance 8 meters from one end. So this is BA, this is C, and this is B. Now in the question, the corresponding 4 kN force is acting right at the top of this center. We have 4 kN here. Then 6 kN will be acting 3 meters from this, and then the next load is 8 kN at a distance of 2 meters. So when it's at a distance of 2 meters, it will be directly on top of this, because the center is 10 meters to the center, and then this is 2 meters here. So as such, you will have the 8 kN load acting on top of section C, and then you have another 5 kN acting at this corresponding center. So this, I'll just write it here. Three meters, 2 meters, 2 meters. Then after 2 meters, again you have a UDL, that is 4 kN per meter. If I count the distance from the center, 2 plus 2 plus 2, 6, and this distance is 4. So it will, this endpoint will reach the corresponding point A. Now, if I draw the influence line diagram of the corresponding section at C, the ordinate, as you know, I'll write it here. This distance it is total 8 meters, and this distance it will be 12 meters. So as such, this ordinate will be 8 into 12, that is 20 minus 8 whole divided by 20, that is equal to 4.8. Now once I have this value of 4.8, I can find the slopes at both these ends, which will be helpful in finding the ordinates at different points. So this will be equal to 4.8 divided by 12, and this slope will be equal to 4.8 divided by 8. Now I need the corresponding ordinates at different points, say at this corresponding section here, at this point, etc. So let me first draw the ordinates. Now write the distances here. 4 meter, then I have 2 meter, 2 meter, 2 meter, 3 meter, then lastly 7 meter, and this corresponding ordinate is 4.8. Now in order to get the ordinates, simply multiply the corresponding slope and the distance from this corner. So 4.8 divided by 8 into 4, just write it down here. 4.8 divided by 8 into 4. That corresponding value will be the ordinate here. So that will be equal to 2.4. This will be 2.4. Similarly, 4.8 divided by 8 into 6. Okay, that will give you a value of 3.6. Now at this end, 4.8 divided by 12 into 7. Okay, that will give me a value of 2.8. Then 4.8 divided by 12 into 7 plus 3, 10 meters. That will give me a ordinate 4. Okay, so as such, you know the corresponding ordinates at these concentrated load points. Okay, so in order to find the bending moment, you simply multiply the corresponding load by the ordinate. So 6 into 2.8 plus 4 into 4 plus 8 into 4.8 plus 5 into 3.6, and this UDL you will have to find the corresponding area of this entire section. Okay, so let me write it here. Bending moment at section C for the given load position, which is equal to half into 4 into 2.4. This is the area multiplied by the corresponding value of load 4 kilonewton per meter plus 3.6 into 5 plus 4.8 into 8 plus 4 into 4 plus 2.8 into 6. Okay, so as such, if you multiply all these, you will get 108.4 kilonewton meter. This is the bending moment at section C. Okay, similarly, you can also find the corresponding shear force. You can also find the corresponding shear force. Okay, let me draw it in another page. So you have again a 20 meter span slab, and this is at a distance of 8 meters. Now I write the corresponding load positions here. This 4 kilonewton, 6 kilonewton, 8 kilonewton, 5 kilonewton, and then you have a UDL. Now this is the corresponding ILD for shear force at section here. ILD for shear force at section C. This distance, it is 8 meters and this distance is 12 meters. So as such, this corresponding ordinate, as you know, it is A by L, that is 4 divided by 20, that will give me 0.4, and this will be equal to 1 minus 0.4, that is 0.6. Now as I told you earlier, I find the corresponding slopes at both these points, at both these lines. This corresponding slope, it will be 0.6 divided by 12, and this corresponding slope will be 0.4 divided by 8. Okay. Now I find the corresponding ordinates at different points here. Okay. Seven meter, 3 meter, 2 meter. Two meter, 2 meter. Okay. So simply multiply the corresponding slope and the distance. So 0.6 by 12 into 7, which will give me 0.35. Then 0.6 by 12 into 10 will give me 0.5, and this corresponding in this end 0.4 divided by 8 into, this is 4 meters, so this will give me 0.2, and 0.4 divided by 8 into 4 plus 2, 6 meters will give me 0.3. Okay. Now as you know, simply multiply the concentrated load by the ordinate, and then you have the corresponding UDL, multiply the area. But remember one thing, this has both a positive and negative value. So as such, this I will mark it as positive and this I will mark it as negative. So in order to find the maximum value, we take the maximum value of positive or the maximum value of negative, depending upon the case. So in this case, positive is more. So as such, to find the maximum value of shear force, I take the corresponding concentrated force multiplied by the ordinates. If it is positive, I will write it as positive. If it is negative, I will write it as negative. So maximum shear force at section C due to the given load position will be equal to, okay, half into the corresponding area, 4 into 0.2. This value as such will be negative, okay, multiplied by the corresponding load, that is 4, again minus, since it is in the negative ordinate, minus 0.3 into 5. Then in the next corresponding value, you see 8 multiplied by, I can either use 0.6 or 0.4, but since I want to find the maximum value of shear force, we see the corresponding area in which the maximum shear force can be obtained, either in the positive side or the negative side. So as such, since the area here is more larger, I take it as positive. So this will be equal to plus 0.6 into 8 plus 0.5 into 4 plus 0.35 into 6. This will give me a value of approximately 5.8 kilonewton. So this is how you find the maximum value of bending moment and the maximum value of shear force. We shall go on to the next topic, value of internal forces. Now I told you earlier that the value of internal forces, whether it is bending moment or shear force, depends upon the position of the corresponding loads on top of a beam. So in the earlier question, it was the corresponding position of loads was given at a particular point, and then we were asked to find the corresponding value of bending moment and shear force at a section. Now sometimes what happens in the question is that they will give you a corresponding section, okay, and they will ask you to find the maximum value of bending moment and shear force for any position of load, okay. So you have to find the corresponding maximum value of bending moment and shear force at a section where the loads may be at any position. Rather than specifying the load position, load can be at any position. So in order to get that picture in mind, let me tell you one thing. Any corresponding in a simply supported beam, the corresponding internal force, whether it is bending moment or shear force, it depends upon two things. First, the load, whether it is a UDL or a concentration or whatever it is, and the corresponding position, okay, the load and its position. And then it depends upon the corresponding which section you want to find the corresponding value of bending moment or shear force, okay. Now as I told you, the next part we shall be going is to find the maximum value of internal force, okay, at a corresponding section, okay. So if you have a corresponding beam like this, okay, if you have a section like this, a section C here, now if a train of loads pass this corresponding bridge or this slab, okay, at one particular position, this corresponding section will have a maximum value of bending moment and a maximum value of shear force. So what is that maximum value? What is that maximum value? So the maximum value of internal forces, that is what we shall discuss at a particular section, okay. Now in case of a series of loads that are concentrated, okay, the maximum value of internal force, okay, occurs when the corresponding concentrated load, okay, is placed at the maximum ordinate. For example, if I have a beam, if I say this is a simply supported beam like this, and say I want to find the corresponding value of bending moment. So if I draw the corresponding ILD, it will be like this, okay. So in order to get the maximum value of bending moment, what I do, I place, you see, if this is P1, P2, P3, etc., okay, I place the corresponding load maximum of this, okay, P1, P2, P3, such that it is directly on top. Say for example P2 is maximum, so this will be P2, this will be P1, and this is P3, okay. So I'll get the, if I multiply this corresponding load by this corresponding ordinate, I'll get the maximum value of bending moment, okay. I'll maximum value of bending moment when the entire load is passing from the leftmost point to the rightmost point. This corresponding train of loads passes from left to right at one particular position when P2, since it is heaviest, and if it is directly over this ordinate, okay, then you get the maximum value, okay. Sometimes whenever if the corresponding I'll show you a figure here, you see here, you can see here, so there is a train of loads here, and this is the corresponding ILD for a Q, where Q in this case may be, for example, bending moment. So as such, what I do, I have P1 multiplied by this Y max, then P2 multiplied by this corresponding ordinate, P3 multiplied by this corresponding ordinate. Sometimes what happens is that sometimes we'll be able to get the corresponding maximum value. If this say load P1 is very large compared to P2 and P3, then okay, simply place this P1 on top of this coordinate, we get the maximum value of bending moment at a particular section, okay. But sometimes what happens is that when P1, P2, etc. are of comparable values, then we'll have to check for multiple positions, okay. We'll have to check for multiple positions A, B and C, means first P1 is placed, then P2 is placed, then P3 is placed, and then we will have to find the maximum value. So sometimes you may have to go for trial and error method, or sometimes you can get the answer directly, okay. This is in the case of a concentrated force, concentrated loads. Now in case of UDL, there are two cases. In one case, when the corresponding UDL is longer than span, that means the entire beam is having a UDL. For example, if you have a dead load, the dead load usually will be there throughout. So as such, we can consider dead load to be a UDL. So there is one case when the UDL is throughout the span. In that case, for maximum positive value of the quantity, take only those portions that are covered by the UDL where ILD is positive. Let me tell you one thing. For example, if you have a beam like this, okay, and then I am finding the corresponding maximum value of shear force, say, at this section. So I have corresponding shear force ILD like this. Okay. Now, in order to find the maximum positive value of shear force, I place even though the UDL is there throughout, I place the corresponding value of UDL only here. Okay, I place the corresponding value of UDL only here. Say that maybe positive side or maybe the negative, whichever is maximum. Okay, and then I find the corresponding value. Maybe maximum positive shear force and maximum negative shear force. Depending upon that, I can get it. Okay, so as such, we don't place it full, because when you place it full, what happens is that this plus, and then when you take this also, this will become reduced. So in order to avoid that, what I do, I take only the corresponding positive value. Okay, so when the UDL is there throughout, okay, we take only the corresponding positive value for determining of the maximum value. Now sometimes we have UDL shorter than span. Okay, so in that case, for finding the maximum positive value, the corresponding load should be placed in the neighborhood of the maximum ordinate, such that these corresponding equations get satisfied. So as such, if I have a UDL that is shorter than span, as shown in the figure here, okay, and I have a large beam here, and this is the corresponding ILD of this beam. So I have got here a maximum Y max, and then I have YR towards the right side and YL towards the left side, and this is the corresponding UDL. Okay, this is the corresponding UDL. So anyway, this corresponding UDL should be placed somewhere in the neighborhood of the maximum ordinate. Okay, now in order to find the corresponding value of YR, this corresponding equation, okay, YR equals Y max minus CSL into SR minus SL plus SR, where SL and SR are the corresponding slopes at these sides. So if you get this, if you simply substitute these values, and C is the corresponding total length of the load here, if you get these values, you will get the value of YR. Okay, you get the value of YR. So once you know the value of YR and then Y max, I can obtain the value of Q max by this equation. I'm not going to the derivation of this part. Okay, so as such, if you find the value of YR, then Q max equals YR plus Y max by 2. Okay, into C, where C is the corresponding length of the load and Q is the intensity of load. Q per unit length. Okay, that is how you find the corresponding maximum value of internal force at a section for any corresponding position of load. The position of load may not be defined. Okay. So as such, when in an examination, you may have three types of problems. Okay. In the first case, the train of loading means the different points of loading, the train of loading, what you call, and the corresponding position of loading will be mentioned, and you will be asked to find the bending moment and shear force at a section. The second thing is only the train of loading is given. Okay, and then you will have to find the maximum bending moment and shear force at a section. Okay, you will have to find the maximum. The position will not be given. So you will have to look for all the possible cases. Sometimes you may require trial and error. Sometimes you may not require. Depending upon that, you have to look at all the possible cases and find the maximum value of bending moment and shear force. The next is absolute maximum value of bending moment and shear force. Absolute maximum value of bending moment and shear force means throughout the corresponding beam, there is one section in which the bending moment is maximum, and there is one section in which the shear force is maximum. Okay, so what is that maximum value of bending moment and shear force? At one position you have, at one section, not position, at one section you have maximum value of bending moment, and throughout, if the entire train moves from, or entire train of loading moves from left to right, okay, at any one section throughout the beam, you have a section in which there is the maximum value of bending moment throughout for any position and the maximum value of shear force. So what is that value and where is that section? That is the type of problem, third type of problem you will get it. Okay. Now, in earlier problem what we had done is that we had learned to compute the maximum value of shear force and bending moment for a series of concentrated loads at specified positions. But from a design point of view, what it is that it is important to get the critical location. That is what I told you. We have to get the critical location or the corresponding critical section where the bending moment or shear force is the maximum value when the corresponding plane of load passes throughout from left to right. Okay. So this corresponding maximum value can be obtained by identifying the position of loads analytically. How do you find it? Now this I am talking only of a simply supported case. Okay, there are a large number of cases and it's not possible to derive such formulas for all cases, but this I am telling for only an absolute maximum value for a simply supported. I use the word, you see there is a difference, I use the word absolute. So absolute maximum value of internal force for a simply supported beam. We will be talking only of a simply supported beam. Now for a given train of concentrated loads on a simply supported beam, the maximum value of shear force occurs at the support. Okay, so the maximum value of shear force as such will be at support. Okay, so as such what we do, we draw the corresponding ILD for the reaction at support, and then we place the corresponding train of load at particular positions. Maybe you will have to check for 2 or 3 trials. You will have to check for 2 or 3 trials, and then we obtain the maximum value of shear force. Okay, that will be usually at the corresponding support. Now, if you want to find the maximum value of bending moment, now maximum value of bending moment, if you have a train of loads, will occur under a load Pi. When the center of span is equidistant between the load Pi and the resultant R. That means if I have a series of loads like this, okay, I find the resultant of this load. Okay, and in order to find the maximum value of at this corresponding Pi position, I place the corresponding train of loads in such a way that it is at the center. It is the corresponding Pi and R are equidistant from the center. Okay, so if the distance between the point Pi, the load Pi and R is D, okay, and then this corresponding should be positioned in such a way that x is equal to D by 2. You may not get this idea very clearly unless you solve a problem. So we will do a problem after this, and then you will get the proper idea of how you can do it. Okay. Now even in this case, what happens is that we will have to look for multiple positions. So Pi can be this, Pi can be this, Pi can be this, any of these as such. So we will have to look for multiple positions or possibilities in order to find the maximum value correctly, maximum value of bending moment. Now for a general case, so far I have been talking of a simply supported beam here. Except for a few simple cases, it is very difficult, underline this one, it is very difficult to formulate rules for finding the absolute value of maximum quantity. Okay, especially in the case of continuous members, it's maybe not be possible. In such a case, what we do is that we develop the corresponding influence line diagrams for maybe shear force or bending moment at different points throughout the length of the bridge. And then what we do, we develop an envelope, we develop a line connecting the maximum points. Okay, this corresponding thing, if you as such, will require too much time as such, because it is not possible for us to find the corresponding bending moment and shear force at each and every section, okay, for different positions. So what these things, usually it is done by computers, by built softwares, where they use these corresponding ILDs and superimpose them and get the maximum envelope, and then from that they find the maximum value of bending moment and shear force. Okay, so that part is usually done by computers. As such, we are not going to much detail, but as such we shall solve a small problem here. Now this is a simple problem here. Find the absolute maximum shear force and bending moment due to a moving load shown below over a simply supported beam of 40-meter span. So we have to find the absolute maximum value of bending moment and shear force. So in this case, let me first find the corresponding center of gravity of these loads. Means the corresponding resultant of these loads and where it acts with respect to this leftmost point. So the position and value of the resultant. Okay, resultant. Okay, this, the center of gravity, we may call it center of gravity. Some textbooks call it center of gravity. Will be equal to. So I can obtain this as 200 into 2. This corresponding load 50 into 0 plus 200 into 2 plus 100 into 5 whole divided by the total load, that is 50 plus 200 plus 100, that will be equal to maybe 3.143 meters. That means the corresponding resultant here, the corresponding resultant of all these loads, I can consider all these loads at one single load. The resultant of all these loads can be considered as a single R acting at a distance of 3.143 meters from the left end. So from the right end it will be equal to 3.857 meters. Okay, so this we will have to first find it. Now we are finding the absolute maximum shear force. Absolute maximum shear force. Now we know that the absolute maximum shear force occurs at support. Okay, so if I have a 40 meter span B, okay, then the ILD for the corresponding reaction at say A will be equal to like this. It will be like this. Here you have the ordinate 1, ILD for RA. Okay. Now what we do in this, we have to place the corresponding concentrated strain of loads. We do 50, 200, 100. So the distance is 2 meters and 5 meters. So as such, you see, we'll have to place this corresponding loads at different positions. The first position will be like this: 100 here, 200 here, and 50 here. Okay, this may be one case, but anyway it will be much smaller. Okay, you will not get much of a value. So this will never be the case. Okay, so this case I can ignore. Okay, next case will be like this. The same thing I am drawing here. Here 200 will come here. Then you have 100 here. And then you have 50 here. This is another case. Okay, and this is 1. This is 2. Okay, this one anyway it will not be there, so I am not finding it out. In this case, the corresponding the shear force as such will be equal to 200 into 1 plus, you see the total length is 40. So this corresponding slope will be 1 by 40. So 1 by 40 into this corresponding coordinate here, total length is 40, so this length will be equal to 35. So 140 into 35 into 100. So this corresponding value will 287.5 kilonewton for position 2. Okay, next we go to find the third position as such. So here you have 50 kilonewton, 200 kilonewton and 100 kilonewton. Okay, so if you find the ordinates here, this is 2 meter, this is 5 meter. So as such, this length will be equal to 40 minus 7, 33, and this length is 5 and this length is 2. So as such, shear force in this case will be equal to 50 into the ordinate here is 1, 50 into 1 plus 200 into the slope here, so you know it is again 1 by 40. So 1 by 40 into the corresponding distance is 38 plus 100 into 1 by 40 into corresponding distance is 33. So this will give me an answer 322.5 kilonewton. Now there may be a position in which there is a reverse chance, okay, reverse chance in which the corresponding 100 is here, 200 is here and 50 is here. Okay, that is also a possible chance. Okay, so if you find the corresponding value in such a case, okay, you get 100 into 1 plus 200, as this distance is 5 meters, 2 meters, so 200 into 35 by 40 plus 50 into 33 by 40. So as such, this corresponding value will give me 316.25 kilonewton. Similarly, when this 200 is on top, 100 is outside, so as such you may get a value. In that case, the shear force will be equal to 200 into 1 plus 50 into 38 by 40. So you get a value of 247.5 kilonewton. And there is one position in which 50 is here, that will be anyway smaller, so that we will neglect it. So as such, you can see that this corresponding load position, okay, this corresponding load position will have the maximum value of 322.5 kilonewton of shear force. Similarly, you will get the same thing at the corresponding other end of the support also. Okay, so this is how you find it. Okay, this is how you find the absolute maximum value of shear force. Next, we find the absolute maximum value of bending moment. Now I hope you remember the corresponding case by which you can find the corresponding maximum value of bending moment. We said that if you have a train of concentrated loads, there should not be any other loads beside the concentrated loads. Now if I have, say for example, a beam like this, that is 40 meters, and I have the load, this corresponding is the center. Okay, so this corresponding distance is 20 meters. You have a train of loads, say for example, in the figure it is given, this is 100, then you have 200, and then you have 50, 2 meters, 5 meters. Okay, and somewhere the resultant is somewhere here. I shall draw the resultant like this, and it is 3.143 meters from the left hand and 3.857 meters from the right end. Okay, so what I do, there are three possibilities. Okay, the first thing is that I place these loads in such a way that this corresponding C lies equidistant between R and 100. Then the second case is that I place the corresponding load in such a way that this point C is equidistant from 200 and R. Then I place the load in such a way that this point C is equidistant between 50 and R. Okay, and then you find the corresponding value of bending moment, and among these three possible cases, which is the maximum, we find it, and that would be the absolute maximum value of bending moment. So as such, let me go to each of these cases separately. Sometimes what happens is that we may not need to take all of these cases, okay, depending upon the corresponding position of loads. For example, in this question here, the case in which the corresponding position of loads in which the point C is equidistant between 50 and R, okay, the chance of getting the maximum bending moment in such a case is less. Okay, there is more chance when C is equidistant from point 200 and R, and when point C is equidistant between point R and 100. Okay, so as such, sometimes depending upon the understanding of the problem, you can avoid some of these cases. Okay, so as such, we shall go into each of these cases separately. We shall first go to case 1. You have the corresponding 40-meter beam here. Okay, now this is the center, which is at 20 meters. Okay, now you have the train of loads in such a way that the corresponding resultant is at a mid distance between R and 100. Okay, and then you have the rest of the loads like this, 50 kilonewton. Okay, so as such, the value of R as such will be equal to 350. Okay, sum of all these loads, and you know this distance. This distance, total distance is 3.857. 3.857. So this distance between this load and C, the resultant R and C and 100 will be 3.857 divided by 2. Okay. Now when this is the resultant R here, this distance will be equal to 20 minus 3.857 divided by 2. Okay. Now the bending moment under load 200 kilonewton, that is first we'll have to find out, and then you have to find out bending moment under load 100 kilonewton. There is no need of finding bending moment under load 50 because it will be very small. Okay. Now for both of these, I'll need to find the corresponding reactions RA or RB, any of these. Okay. Now here I can find, I hope you understand the concept of finding RB. If I have a beam like this, okay, you have the resultant R here, that is 350, and on one end you have this corresponding distance as 20 minus 3.857 divided by 2, that will be equal to 18.072, and the other you have some other distance. So I'll find any one of these is sufficient, so I'll find the value of RB. Okay, so RB is equal to 350 into 18.072 whole divided by 40, which will give me 158.13 kilonewton. Okay, that is how I find RB. Now bending moment at under load 200. Okay, M, I'll write here M 200 to understand that. That is equal to 158.13 multiplied by the distance between 200 and this corresponding reaction RB. Okay, now you see you have the center 20 meters plus 3.857 divided by 2, that is 23.072. so into 23.072 minus 100, this corresponding load 100 into the distance from 200, that is 5. That will give me an answer of 3148.375 kilonewton meter. Now the second case is BM under load 100 kilonewton. That will be equal to this corresponding RB 158.13 multiplied by the distance from this corresponding point to this. So that will be equal to 20 minus 3.857 divided by 2. Okay, that will give me a value 2857.77 kilonewton meter. Okay, these two answers we have to find the corresponding loads at under 200 and 100. 50 is not required since it will be lesser. Okay, this is for case 1. Similarly for case 2. We have the 40 meter span here. Then you have the 20 meter at center. A 20 meter at center. Next, the corresponding load should be placed in such a way that the center point C is between the resultant and 200. So you have here 50, you have here 100. Okay, now you know that this corresponding distance will be equal to 3.143 minus 2 equal to 1.143. So this distance and this distance will be equal to half of that. That will be equal to 0.572. Okay. So this distance here will be equal to 20 minus 0.572. Okay. So as such, first I find the reaction. I will find now the reaction RA. That will be suitable for me. As such, I have only one load here. So RA, I want to find the corresponding here two cases. Bending moment under load 200 kilonewton and second one bending moment under load 100 kilonewton. Okay. So as such, I think I will find either RA or you can find both, depends upon your convenience. So here RA will be equal to and this distance here will also be equal to 20 minus 0.572. If you want to find the corresponding reactions, okay, for the time being I will find reaction RA. So this distance, this R, this will be 20 minus 0.572, that will be 19.428. Therefore RA, this is RA, therefore RA will be equal to 350 into 19.428 whole divided by 40. This will give me an answer of 170 kilonewton approximately. Okay, so the bending moment under the load 200. M200 is equal to 170 kilonewton multiplied by this distance 20 minus 0.572, that is equal to 19.428 minus this corresponding distance 50 into 2. This will give me answer of 3202.76 kilonewton meter. Similarly, I can find under the 100 kilonewton load. So M100 as such will be equal to 170 multiplied by this distance 20 plus 0.572 plus this distance, that is 3.857 minus 50 into 7 minus 200 into 5. So as such, if you check this, you will get the answer 2802.93 kilonewton. Okay, so you can see this is the maximum value in this case. In the earlier case, under 200 it is the maximum value. Here also 3202 is the maximum value. Coming to case 3, you have 40 meter span beam here. You have the corresponding midpoint C here. This is 20 meters. Okay, I place the load in such a way that the corresponding 50 kilonewton is equidistant from C. The corresponding point C is equidistant from 50 kilonewton load and the resultant R. So it is equidistant here, and then you have here the 100 kilonewton load. Now you have this distance as 3.143 meter. So half of this will be equal to 1.572 meter. That means the corresponding 200 kilonewton load will be somewhere here. Okay. In order to find the corresponding reactions, either RA or RB, first I think I will do RA here. So I will find this corresponding distance. Now this corresponding distance will be equal to, this is 20 meters. So 20 minus 3.143 divided by 2, or 20 minus 1.572. So if I draw here separately, here is the R. This will be 20 minus 1.572. I will get as 18.428. 18.428. This is RA. This is RB. Therefore, RA will be equal to 350 into 18.428 whole divided by 40, which will be 161.25 kilonewton. Okay. Now, bending moment under 200 kilonewton load. M200 will be equal to 161.25 multiplied by, now the distance you have, now the distance from this corresponding point to here, to point, that will be equal to 20 minus 1.572 plus 2, that will be equal to 20.428 minus 50 into 2. This will give me an answer of 3193.92 kilonewton meter. Now the second case, BM under 100 kilonewton load need not be taken, since it will be anyway be lesser. Okay, so this need not be recorded, it will be anywhere lesser. So if you try to subtract it, it will become very less. So as such, you got these values. So from here you can get 3193.92. then 3202.76, and then 3148.375. Therefore, maximum bending moment will be equal to 3202.76 kilonewton meter. The answer. Now, depending upon the number of cases, one or two may be ignored. Okay, that depends upon this. The same problem as such can also be solved using influence line diagrams. Okay, if you want, we'll maybe I'll take an additional lecture regarding that part.